Hi, everyone. This is Guan Ying. I come from UC Davis, and my poster is about build an OMFIT module that can be used for ECEI data protocol analysis and for radiation modeling. So I'll start with some motivation. ECEI is a powerful 2D electron temperature fluctuation measurement diagnostic. So it can measure MHD and turbulence. In this case, I show MHD case. We have alpha angle mode. This is spectrogram, and this is a 2D image of the alpha angle mode. And this is the synthetic image of alpha angle mode. So basically, we hope that we can build a module that can process the raw ECI data and get to this image and image analysis. So because it is an imaging diagnostic, it can have lots of useful outputs. For example, the turbulence dispersion, frequency versus wave number, the turbulence velocimetry, and the radial mode structure, the deployment mode structure, and so on. So this is a module we're going to build. So for those advanced features, we can use some codes and scripts in the module to process that. So anyone on D3D can use this feature. So we designed module for 3 needs. The basic need is to, we need to know where ECI is, do spectrogram, do 2D image, then develop some advanced algorithm to extract the quantitative information from the image, like the plot mode number, radial wave number, turbulence dispersion. And last, because EC radiation is not ideal in some cases, we need to understand EC radiation and run the forward radiation code using the module. So this is a basic feature about data processing. You start with picking a target shot, and the module will go through the logbook and find if the data is available and what's the hardware setting. And then you can use hardware setting to map the ECI using OMFIT and check spectrogram and do a design digital filter and plot to the image. And the module also has some advanced features. This one, it provides a very high quality spectrogram using the ECEI algorithm, meaning that because of the plasma thermal noise, the spectrogram characterizing those alpha angle modes is noisy. Because you can see noise in the background, but what really the mode is those red lines. So using the algorithm, you can find that all the background noise is smoothed out because the algorithm will use all the ECI channels, and those channels will cancel the plasma thermal noise. And the radial mode structure of alpha angle mode is very important because it's associated with transport. So from 2D image, we can develop algorithm that can extract this information by combining the straight line coordinates of the tokamak and area measurement at each channel and fit the best possible plot mode number and radial wave number of an alpha angle mode. And for this pedestal, broadband, and MHD, we can use a 2D image to see the downward propagation and plot wavelengths. And quantitatively, we can use this frequency versus plot wave number plot. So what you see here is the dispersion of this turbulence at pedestal. And what you see here is turbulence propagating downward. The slope of this line is the phase velocity. EC radiation is not ideal. So here we can discuss the resolution of the system using the OMFIT module. In this case, we're looking at the plotted resolution. So so this is R and Z. We have this 2D image of assume a 2D image of turbulence. We use 3 channels, black, yellow, and red, to plot the waveform, the time waveform of the turbulence. For this low K turbulence and for the high K, we can also plot it. So, and this is the waveform of the measurement. Basically, the solid line points to the low K turbulence, the dashed line points to the high K turbulence, And what you can find is that the solid amplitude is stronger, much stronger than the dash amplitude, even though the input amplitude are the same. That means because of the finite product resolution of the system, we are not really sensitive to high K turbulences. And here let's discuss the residual resolution of the system. Assuming we have this 2D image and we have this kind of mode width, I will gradually narrow down the mode width and see the measured radiation change, right? So here we have normalized minor radius, and this is KEV. Input profile is a bomb structure. Just look at this green curve, green solid line. Its background is 2 keV, and then at mode location suddenly increase to 2.5 keV and suddenly drops. So I will gradually narrow down the mode width and see how the radiation profile change with it. And the radiation profile is the dots. So basically, when mode width is very narrow, it's about 15 millimeters. Using the wide zoom ECEI, we will see this red dots. Means that this radiation amplitude is much smaller than the original amplitude. And if we can use the narrow zoom ECEI, that's another. So narrow zoom and wide zoom are two different bandwidth setting of the ECEI. So you can see the measurement amplitude is much closer to the original one. So it means narrow zoom ECEI has better resolution, visual resolution than the wide zoom ECEI. That's the summary. We develop OMFIT module. You can use it to access ECEI data to do simple data analysis. And there are also advanced features to fit the radio mode number, point mode number, radio structure, and the high quality spectrograms. And the module can also do radiation modeling to evaluate the spatial resolution of the system. Thank you very much.